We're going to start with talking about mole to mass conversions. I know that I gave you a few problems that were doing moles to particles that you should have submitted, but I also want to do some mole to mass. So let's revisit where we get the mass of an element. So if you look at the periodic table, right, where do we find the atomic mass? Which of these parts of the chemical symbol on the periodic table gives us the atomic mass? So real quick, let's just define atomic mass, right? So atomic mass is the average mass of all isotopes of a specific element found in nature. So for example, carbon. Isotopes of carbon that exist in nature are carbon 12, carbon 13, I believe there's carbon 14, I don't think there's carbon 11 though. So of those elements, there's a certain percentage in nature that it's carbon 12, carbon 13, carbon 14 of all the carbon atoms in the world. That average mass of all of those comes out to be 12.01. So the majority of carbon in nature is the carbon 12 isotope. So then we get this unit of 12.01. So you know what all those represent, but 12.01 is the atomic mass. What is the units we use with atomic mass? It's atomic mass units, or AMU. So let's talk about then what the molar mass is. So the mass of 1 mole of an element or a compound is its molar mass. Okay, so very similar to the atomic mass being the mass of 1 atom of an element or 1 unit of a compound, the mass of 1 mole of an element or a compound is its molar mass. So 1 mole of hydrogen has a molar mass of 1.01 grams, whereas 1 mole of gold has a molar mass of 196.97 grams. So very different amounts of mass, but we're looking at the same amount of hydrogen and the same amount of gold, right? So same number of particles, but because hydrogen atoms weigh 1.01 AMUs, and each gold atom weighs 196.97 AMUs, the molar mass of each, it's exactly the same number, but we give it the unit grams instead of AMU because grams is a measurable amount. And when we're taking 1 mole of gold or 1 mole of hydrogen, the same value for its atomic mass units, the same number value, will be equivalent in grams, which is really convenient. So we can just use the periodic table to identify what the molar mass is. So again, how do you get the molar mass? Look to the periodic table. You're going to start by identifying for elements the atomic mass value, and then just change units from atomic mass units to grams, right? Don't put AMU at the end, put grams. And 1 mole of, say, like I gave the example of hydrogen, is 1.01 grams. When it comes to compounds, you need to find the molar mass for each individual element. If it's, say, water, where you have H2O, you have to look at the subscript 2, and you're going to have to multiply that molar mass you found for hydrogen, since there's 2 hydrogens in it, and multiply it by 2. Then add that with the other elements' molar masses, so the oxygen, for example. Okay, so it ends up being 1.01 times 2 plus 16 or 15.99, right? So, my bad, but the molar mass of this element, right, it's 107.868 AMUs on the periodic table, so 1 silver atom weighs that on average. And then if we look here, we got 107.868 grams per mole, or another way of writing this is 107.86 grams is equal to 1 mole of silver, right? So this is kind of just a way of writing it, and you're still showing this fraction, right, that 1 mole of silver is equal to 107.868 grams, okay? Now, what about this compound? So we're looking at AgNO3, or silver nitrate. Okay, how do we find the molar mass of this compound? How do we calculate that? We take silver's mass, we got 107.868, plus nitrogen, there's 1 nitrogen, right? So 14.01, plus, we have to put a 3 and then multiply it by oxygen, which is 15.99, right? So essentially you have to add up those masses together to get the molar mass of silver nitrate. Okay, so in this case we got 169.87 grams equals 1 mole of silver nitrate, right? And we can obviously write two different fractions with that. So let's do some practice problems. I want you to use dimensional analysis and try these problems. So if I have 103 grams of aluminum, how many moles do I have of aluminum? So how do you set that up? Remember, just start with the value you're given, with the units you're given, and then remember you got to cancel the units that you start with, right? And in this one we're going from grams to moles. Keep that in mind, okay? Number 2, what is the mass of 1.2 moles of silver nitrate? In this problem, you're starting in moles, right? And you're going to the mass or grams, right? So you're going to have to get the molar mass of silver nitrate. Conveniently, I've already solved that for you. Number 3, it wants how many grams of water there are in 13 moles of water. So 3, you're going to set up like 2. You're going to start with the number and unit you're given, which is in moles, and you're converting it into the mass. Okay, so why don't you try each of those problems, and then once you're finished, you can check the solutions here. So here are the solutions, or here are the problems set up. 103 grams of aluminum over 1 times 1 mole of aluminum over 26.96 grams of aluminum. Number 2, you start with the 1.2 moles of silver nitrate over 1, and you multiply it by 169.87 grams over 1 mole of silver nitrate. And then the third problem, you start off with 13 moles of water over 1 times 18.01 grams over 1 mole of water. Okay? And now let's look at the solutions to each of these problems. The first problem, 3.82 moles of aluminum. The second problem, 203.8 grams of silver nitrate. And the third problem, 234.1 grams of water. To put this into perspective, the average adult human weighs about 65,000 grams. That's about 140 pounds. Okay, so just look at that for a second. 13 moles of water, right? 13 moles, so it's a measurable amount for us in the lab. It's still only 234 grams, whereas a human is 65,000 grams. So I could do another problem. How many moles of water are in the human person if the average human person weighs 65,000 grams, right? You could do that math. So what you've learned in this section, what the mole is, that the mole relates to both amounts of something, and the mole relates to the mass of specific things because it has a specific amount that does not change, aka Avogadro's number. There's always 6.02 times 10 to the 23rd things in 1 mole of it. But then you also learn that the mole can be used to convert between the amount of particles and the mass of particles. And we can kind of sum up our conversion factors that we've created or should be able to use at this point between this figure or with this figure. So the mole is at the center, right? We can move between the mass to the number of moles, and we can move from the moles to the represented particles back to moles. Okay, so if we want to go from represented particles to mass, we got to go through the mole. Okay, and as you can see, these don't change. These are going to change based on what the molar mass is of the substance that you're looking at, okay? So these conversion factors, they're always going to be the same except for your unit here, particles will change. And over here, the molar mass is all that's going to change. And that concludes section 10.2.